Was with the official sound test, testing, 1, 2, 3, testing. Okay, if we're good to go, I will start. Hi, my name is Roxana Cremer. I'm a PhD student at Stockholm University in the Department of Environmental Science, and I have a background in metrology. We are focusing mostly on aerosol science. So quickly about aerosols, you may have heard about them in the last 1.5 years, since this specific virus is also considered an aerosol particle. But in my department we mostly focus on the Arctic regions and all kind of aerosol types that come up there, and my specific aerosol is black carbon, or maybe a little bit more general you would call it soot. That's basically whenever you put anything on fire, be it a piece of paper, a candle, a toaster, when every time you have some heat and it's generating or can generate some more heat, black carbon is produced. And the most or the biggest, largest contribution sources at the moment are fossil fuels on an industrial scale, and cars, for example, are a big source, and the most important natural source are forest fires. And I will talk a little bit more about forest fires, since they came a little bit more to our attention, I think, in the last 3 years. So forests are basically very big ecosystems. It's a biosphere, and they store and contain a lot of carbon materials in a biological organic form. Actually, more than 30% of our landmass on the Earth is covered in forest, or was covered in forest. It's about to change a little bit, but it's one of the biggest lands covered. And when we have a forest fire, in the latest years, only 4% of them actually have natural causes. So natural causes for forest fires would be a dry period, and then a thunderstorm happening and lightning puts them on fire, or you have very high temperatures and it starts on the ground, or with dry periods, or also volcanic eruptions can cause forest fires. But over 90% of the forest fires we have at the moment are man-made, and they mostly happen because we're just not cautious enough with our surroundings. Be it a cigarette butt that you just throw out in the nature, or a bonfire that you don't put out properly in the forest. But can also be on a larger scale, like sparks from an electrical or train light. And catalytic converters of cars or motorcycles that are just put in the forest over dry soil and leaves can actually start a forest fire. There are basically 3 steps of forest fires. So you have one on the ground. That's just when dry leaves or needles start to fume and then form a fire. They are normally easily contained when you build lines of already like burned out areas, or with wetlands. You can stop them relatively easily. Obviously not always, but easier than the treetop fires. When you have as I just said, the treetops on fire, they're way heavier to extinguish. Then you need the airplanes or a helicopter dropping water from above, and that's normally on a larger scale. And the third step, and the worst one, is when the whole system is on fire. And that's what's happening at the moment everywhere in Europe, in Canada, in Australia, that the whole system is on fire, and then it's very hard to manage or even contain into specific areas. And why we talk about forest fires or have a little bit more research going on there is because it's becoming more and more often, more and more forests getting destroyed. And as you can imagine, it actually takes some time to restore a forest system. So when we talk about climate change and the effect on forest fires, it's mostly the variability in rainfall and temperatures and dry periods that interact to cause them or make them more likely to happen. So variability in rainfall basically means you have more of sudden heavy rains, but not this like streamline rainfall that actually wets the whole system and keeps it wet, but you just have a dry period, then you have a heavy rain, and then you have a dry period again, and that's not very good for the forest system. And then also wind is playing an enormous role. If you have heavy winds, obviously as soon as the fire starts, the wind transports it way quicker, way further. And under climate change, these scenarios could just become more and more often, and if you have too little rainfall or too little low temperatures in the forest systems, the forest itself isn't wet enough anymore. Normally you have a little bit of a micro ecosystem below the canopy, so you have a wet soil, but as soon as this dries out, it takes some time to actually wet all the soil layers again to keep them wet and to keep them not likely to catch fire in any case. So just a little bit of numbers here. So in this year, I know it's not over yet and one season of forest fires is still to come, but 24,000 hectares are already burned down all over the globe in 2021, and that's already 20% more than in our last record year, which was last year, 2020. And if you want to see how long it takes to actually recover from a forest fire, especially when you do it naturally without planting trees, you can actually take a day trip to Turista, the national forest south here of Stockholm. There was a big forest fire in 1999. That's now 22 years later, and you can still see the effects in the burned area, and I think most of the trees are about 3 to 5 meters high now, and they are all quite young. And if you want to hear more about how a healthy forest looks like and what kind of trees you need, you should ask another researcher talking about that, because I'm not an expert in that part. And I know a lot of you maybe are thinking about offsetting their carbon, and it's a big part that we are planting more trees over the globe. And obviously they're helping, but it's a very slow system to store carbon. It's also not an endless carbon system, because at some point the tree will stop growing, or maybe there's a forest fire happening, then it's destroyed again and the carbon is again released in the atmosphere. Or it's just cutting down for furniture or, I don't know, bonfire wood. That's also a possibility. So we need to make sure that we build a forest properly and we mix the tree kinds. So you shouldn't have monocultures of just one kind of tree. You should check that there are several that are resistant and can make a nice ecosystem. And also you need to consider the type of soil you have in the region where you're planting trees. Here, for example, in Sweden, you can see often that there's rocks covered with a little bit of soil. So that would make it impossible to get a tree that needs deep rooting into the soil, because there's just not enough soil layer on top of the rocks. In other regions, you have a lot of sandy soil, which then doesn't hold up the water that well. So then you also need specific trees to actually be able to grow and live in that area. Let's see, prevention for forest fire is basically just to educate people and install early warning systems, so you catch a forest fire as soon as it happens and without making too much damage. And that's basically the only solutions we came up with yet to prevent them from happening, and even that one wouldn't prevent for like natural cause forest fires. Then only the early warning system can help to contain the forest fire to a smaller region. So now I'm coming a little bit to my specific research topic, the black carbon I talked about before. It's linked with forest fires because, as mentioned, it always is produced when you put something on fire. So if you have a big forest fire, a lot of carbon is released in the atmosphere, and it's carbon in different stages. So for one time you have the carbon dioxide, which is a greenhouse gas that is released into the atmosphere, but you also have carbon in form of black carbon, organic carbon, brown carbon. That's on a slightly bigger scale. It's still just 100 nanometers, so we can't see it. but it's bigger than the greenhouse gases because it's actually a particle. It is a solid thing. It has a core. But it's not big or heavy enough to be affected by gravity, so it basically just flows around us everywhere. Even now we have black carbon here in the air from all the cars that just pass us by, but we can't see them. But it still makes an effect of our climate system, because the name says that it's black, and if you imagine nice weather, not like we have it now, and you wear a black t-shirt in the sun, you know you're getting very warm and it's heating up quite a bit. You don't want to sit down on a black surface. You look more for like a light white surface or a white t-shirt to keep yourself cool. And that's the same with black carbon. The particle itself is actually black, so it absorbs the incoming sunlight and it warms itself and its surrounding, and actually has a netto warming effect on the climate system when it's just flowing around. Just to make sure I'm not missing anything. So black carbon isn't the only aerosol in the air. We have a lot of different things. For example, in a forest fire you also have they're called VOCs. They're organic compounds released in the atmosphere. The best way of thinking about them is basically when you go through a forest and you have this nice forest smell of like pine. That's aerosols. So you can smell them because they have this component that actually makes them smellable. And they are getting attached to the black carbon until they form a nice round structure. And depending on what is on them, they can fly up higher in the atmosphere and catch some water on them, grow even more, and become a cloud. And we are very much interested in the forest fire in the Siberian area, because whenever we see a big forest fire happening, we can actually track it with a satellite, and you see a big plume happening. You can just see how it's like going around, and then at some point it's spreading a little bit until you can't see it anymore. And we can measure the effect directly on our measurement instruments up in the Arctic, close to the North Pole. So all these particles from Siberia and also from Europe make it all the way up to the North Pole in the Arctic Circle, and can have a major effect there. Because we're coming back to the colors black and white. The Arctic is still quite a white place with all the glaciers and the snow, and whenever you have something black settling on the snow, you disturb the albedo of the place. So the albedo is basically how much sun is reflected back to space. It has a cooling effect. Same with the t-shirt, it reflects back the sunlight, so you're keeping cool, and that's the same what ice and glaciers are doing for our world. So whenever you have something grayish or blackish or even just brownish settling on it, the whiteness reduces and it's getting less and less white, and that also means that the albedo effect is reducing and actually contains more heat, which then can make the ice actually melt. So there are two effects. One is not as much sunlight is getting reflected back to space, which means it's less cooling, and at the same time the ice is melting, which makes it the ground temperature warmer, which then triggers the cycle that even more ice is melting because the ground temperature is warmer. So this effect is actually twice as big. Whenever you have black carbon on a glacier, it melts twice as fast as without black carbon. And that's what we are very much interested in, to see the effects, to observe the effects, because it's not just the forest fire in Siberia that make it to the Arctic. When Canada is burning, most of the particles settle down on Greenland, on the Greenland ice sheet, and melting that one. And it also plays a major role in the Himalaya region, which is also one of our last glacier resorts that we have. And yeah, what I'm doing in my research is basically tracking the transport, how much black carbon comes to the Arctic, what are the main seasons, how is it traveling, is it affected by rainfall, or are there specific pathways that we can observe, and just basically measure and observe the whole system to see how it's changing over the years. to just give everybody an idea how bad actually of a part it is, because everybody of us, when it's weather like this, we make a cup of tea, we sit on the couch, we put on a candle, and we are, as a community, part of the problem. We're not on the scale of a forest fire as is happening, but our cars and fuels make a huge impact, and it's different, black carbon, when you look at it from a natural source or like a traffic pattern. But the effect is the same. We make our Earth warmer, and we make the snow and ice disappear more quickly with our production. Thanks for listening, and if you have any questions, go ahead. I'm just quickly putting that in my bag before it starts raining. Are there any questions? No. Yes. So there's the question about carbon taxes and how much of an effect it has and how you could actually make something like a forest fire in it. And it's a very important thing which I should make very clear. A carbon tax is a measure for the CO2 emissions. This is the greenhouse gas emissions. What I'm talked about is an aerosol particle, which is not included in that one, so it has a different, it's two different subjects basically. So I also can't answer your question of how much of a carbon tax you should put on a forest fire, because there is carbon dioxide emitted, a lot of it, but then it would be also the question, who has to pay it? And I think the carbon tax at the moment is different actually from country to country, and some studies show that 150 euros per ton of carbon would be a fair price, but I think most of the nations are talking about like 60 euros or something, but I'm not sure about that. So unfortunately you have to Google and make your own research, because I can't answer it. Yeah, write to researcher desk when you have any questions. Even when you now see it on the stream, you can always ask a question. We are a big group with different fields, and we can probably find an expert to answer your question. Yeah, any more questions? Yeah, so the question is again about carbon dioxide, the greenhouse gas, and if you can see a rise in the measurements from the forest fires that are happening, and yes, you can see them and you can measure it. Again, it's just not me who does it. Yes. Okay, so we have a question, if you have the equator in the middle of the Earth and the forest fire is happening there, if it travels up north to the North Pole or south to the South Pole. It's actually a very cool question. I'm very happy that she asked that, because you basically have a transport division. Everything that's happening on the north side of the equator basically stays on the north side of the equator, and everything that's happening on the south stays in the south. So I'm not 100% sure about forest fires in Australia or New Zealand where they travel, because I'm not sure about the transport pattern, but they would stay on the southern globe and would probably more end up in Antarctica than on the North Pole, but they're probably settle over the ocean because the Southern Ocean is quite large, and everything that north is north. I mean, especially from Siberia and also Asia, you can see it traveling all the way up to the North Pole within 10 to 14 days. So it takes 2 weeks for them to just make the route through the clouds. Okay. More questions?
As without the black carbon, but how much black carbon has to be there that this happens? Or I guess one particle wouldn't make
So the question is about the glacier and the snow, how much of black carbon needs to settle. I'm actually not sure about the amount that triggers it, but I know there's a threshold, and then it doesn't matter how much black carbon you put on the system anymore. The damage is already done. And I need to check. I don't want to say anything wrong, but it's not as much as you think. So obviously it's not one particle that makes a difference, but normally also it's not just one particle traveling, and it's on the scale of like micrograms maximum, like maybe 0.5 micrograms would already be enough. Yes. So the question is when the black carbon aerosol settles to the ground, if it stays there or if it continues traveling. So as soon as it normally hits the ground, it stays on the ground. You can have wind dust that keeps it up in the air. That's happening, for example, with Sahara dust that's normally blown off by wind into the atmosphere. But I would say in the Arctic, as soon as it settles, it's getting mixed up with the snow and then it stays on the ground. Yes? Per square meter. I should continue to repeat the question, right? So when we talk about the micrograms or of settling carbon or black carbon on the ice sheet, it's normally timed in the square meter. So we always measure per square meter. Yeah. Okay, so the question is about ice coring. If you take an ice core in the Arctic and if you can actually see a layer of forest fires. I'm pretty sure you can see layers of forest fire, especially big ones, because I mean also the Arctic was at one point a forest. That's why we have a lot of coal mining going up on Svalbard, because there was actually a forest that's now a layer in the ground as coal. But I'm not sure in which years or anything, because I'm not an ice coring person. I'm just looking at the air. Yes. That probably depends on the. I have to repeat the question, sorry again. So what happens to the black carbon that is not settled on ice and glaciers, but in other ways of the, or like parts of the Earth? So it probably depends on where it's settled. If it's a bright surface, it would also dim the albedo effect. If it's here in the city with all the asphalt in the streets, it wouldn't make a big difference, because we have already quite a dark surface to begin with. But then also the whole melting process wouldn't happen. It's just the albedo that's then affected. And black carbon or emissions from forest fires are also good, like it's similar to a volcanic eruption. All that comes out, it's also very good nutrition for the ground, and it can go up again in the biosphere. It just takes time. Yeah, so when a forest burns down, then obviously the albedo in that area also changes. So before it's a darker area with green and a different temperature, and if it's burned down, it's maybe not even that darker, but the temperature of the surface is different. It's way warmer because you don't have this like security layer of trees keeping it cooler. You just have the plain area, and then it's normally warmer, and yeah. Yes. So the question is if black carbon has an effect on the ocean. Not in the albedo way, because the ocean is already quite dark. I would assume it just settled and becomes part of the ocean. Maybe it comes back up in the atmosphere via sea spray, but I don't know any. I don't even know if there's a study about that actually. I think it just settles to the ground and stays in the ocean most of the part. Any more questions? Cool, then we can wrap it up in time for the rain to start. Thank you very much for listening.